All right. Good evening, everyone. Thanks for joining. Thank you, Krishna Kumar, for joining. Today, we are going to solve one problem on component matching. By the way, this is the final week of this course, Aeroengine gas turbine cycles. And this week, the problem that we are going to cover is not actually important in terms of your assignments or your exams. Typically, this question will not be asked. But I thought I will cover because we studied a lot of formula in week 12. Therefore, I thought I will show you how to solve one such problem. Now, although you know a brief or a comprehensive understanding of what is component matching, theoretical understanding is sufficient for your exams. Um, but here we are going to solve one problem so that you will be very clear on why we need to do component matching for a turbojet or any gas turbine cycles. Okay. Basically, in week 12, if you look back and think about it, what we studied is we didn't study any new cycle. We just studied a new concept called component matching and also engine performance testing. These are the two things we studied, and mostly theoretical questions will be asked. And it is more obvious, and if you look at the assignment 12 problems. But anyway, we will quickly go through what we studied in this last week. So, um, so till now, for the last 11 weeks, we studied different gas turbine cycles, right? We initially started with the first 2 weeks were like some introduction to the aero engine cycles and introduction to the different components and their thermodynamic analysis, how to do for each and every component. And after week 2, we studied turbojet engines for 2 weeks, and then we studied turbofan engines, and then we studied turbo prop and turbo shaft, right? So overall, are the major cycles that we studied are these four. In addition, we also studied about turbo prop fan, unducted fan, and aft fan configuration. All these things you are very familiar with, right? So maybe quickly I will check my recordings. Okay. So these are the things that we studied, and all these things is for a design point. For example, let's say given the compressor pressure ratio and given the Mach number of the flight and altitude and each component's pressure ratio, for example compressor and fan, and the TT4, if you give all these values, we know how to find performance parameters such as thrust, uh, specific thrust, TSFC, efficiencies. These are the things we understood. These are the things we can find for the given engine configuration. uh, Now, once you design this engine for a particular, condition, you have to. But that engine is also used in multiple other places. For example, if it is a turboshaft engine, if it is, worked in, if you are using it for power generation uh, in a land-based turbine, you may not need all these calculations, even though they need it when they want different power supplies. But when you are installing this in a aircraft, the aircraft is not going to have same ideal conditions everywhere, right? For example, you will have startup, taxi, takeoff, climb, cruise, descent, approach, landing, and all these things will have different flight Mach numbers and will have different altitudes, different pressure and temperature ambient conditions, um, and different thrust requirements. For example, at the takeoff, you need maximum thrust. For cruise, you may not need that much thrust. But what you need is you need to reduce your fuel consumption as low as possible. And similarly, approach and landing, you will have very you typically use the gravity to take care of most of the approach and landing. Uh, so different uh, different sections of your flight profile is going to have different thrust requirements. and the engine that you design we should be sure that the same engine is going to work for all these conditions. For example, taxi, climb, cruise, descent, and landing. So, and the typical flight profile for commercial aircraft and military aircraft, we all know why we need all these things. So, the engine that we design has to be uh, should satisfy all these flight profiles. So, this is how a typical requirements would look like. So, we design it for a design point. For example, uh, this is the engine design point here. Maybe I will use this pen. So this is the engine design point. So maybe what I will do is instead of, I think it's all yeah. So this is the engine design point, and what you have to do is this is the climb to cruise. This is your thrust requirements, how it is going to vary, how the Mach number is going to vary, and therefore you should be clear that uh, this is how your thrust has to vary for your engine. So, for example, the cruise is an off design condition. At the cruise condition, your thrust requirements and Mach number is this much. Okay, similarly, your specific fuel consumption would look something like this. But whether we will be able to get this point from our engine is a question. Okay, so we need to make sure that we can achieve this point with our engine, because we only designed our engine for these two specific points, not these points. Okay. All right. So that is what we are going to do. We try. So the only way that we are going to change the engine parameter is, one of the important way is turbine entry temperature, and the turbine entry temperature is going to vary when you change the fuel inlet. So um, so you used to have this inside the flight. We used to have you know the uh, uh, so to throttle the engine, you need to vary the lever, right? So the lever is going to alter the uh, fuel inlet. So the when you change the fuel inlet, your turbine inlet temperature is going to vary. If the turbine inlet temperature is varying, you know what are the things going to happen. And therefore, if your design point is here and if your cruise point is here, you have to vary the turbine entry temperature from 1400 to maybe 1250 Kelvin, and at Mach number at this point. Okay. So, but we need to know what is the for the cruise condition, what should be my turbine entry temperature, so that I can reach that specific fuel consumption, with in addition to achieving the thrust requirements for that Mach number. Okay, so that is what we are going to do today, component matching. So you will be given the design point and design configuration of an engine. What you should do is you should find this throttle setting, maybe for the off design point, for example a cruise. Okay, so that is what we studied, and for that we basically matching is done by conservation of mass and moment energy between different engines. So the reason is, once you pick a design point, your area size of the engine is fixed. So therefore, you do not have control over the area. You have only control is TT4. So what you have to do is, when you change the temperature, your work output from the turbine changes, and if the work changes, then the compressor work changes. If the compressor work changes, we know the compressor pressure ratio also changes, and if the pressure ratio changes, then the pressure rise will also be different, and therefore the exit thrust is also different. So the only connections that you see here is the mass conservation and the energy conservation, the compatibility between the turbine and the compressor, the increase in mass flow rate in the increase in fuel flow rate will increase the overall mass flow rate, and that is going to affect the nozzle performance. So therefore, the main two conservation principles that we are using here is mass and energy conservation. So momentum conservation must be satisfied. That is what is thrust is developed by the engine. Okay, so that is the main thing. So these are the three conservations that we are going to do for each and every component. And when you do this matching between these components, you will end up finding the compressor pressure ratio that you will have, and also the TT force setting that you need to have to achieve the thrust. Okay. All right. So we will also get a corrected mass flow rate map. So that is coming from, so for example, we will have compressor map and turbine map, and that is coming from the compressor and turbine specifications. Okay. So once you design the turbine and compressor, how we will vary the pressure ratio versus mass flow rate is given by the compressor itself. Okay. So when you change the pressure, how the mass flow rate is going to vary, it is given by the compressor and the turbine. We will use that information to find out what should be the PT4 setting. So for that, we kind of defined a lot of new parameters: corrected mass flow rate, corrected shaft speed, fuel flow rate, thrust, and corrected thrust specific fuel consumption. And we kind of did the mass flow rate and energy conservation matching between different components. First is inlet compressor matching, and we did similarly compressor combustor matching. Anyway, I will go through this again. And we also did compressor combustor turbine, and then turbine nozzle, and then compressor turbine matching, combustion chamber turbine matching, and also turbine and nozzle matching that we did, right? So uh, with all this, we will find the operating line across which we should operate our and across which the throttle has to be varied so that you will achieve the required thrust and specific fuel consumption for that off design point. Okay, so that is the main idea behind this, um, and it is going to be an iterative process the way we are going to solve it. So I will show you how is that. And if you have an afterburner, then you additionally have the afterburner as a component, and therefore you should match the afterburner nozzle and turbine afterburner matching. So that is also we will have to do. Uh, so in today's problem, I'm not going into afterburner, but you can always do it. And then finally, as part of concluding this entire uh, thing that we studied, we typically focused only on the thermodynamics of the Aeroengine gas turbine cycles. But in general, for a manufacturer, they also need to test the engine. Uh, Theoretical calculation is not sufficient, right? We need to find out whether the components that we designed has uh, achieved whatever we achieved our requirements, right? Uh, so there are some principles of engine performance. So basically, these are theoretical, uh, and I hope you would have you would have got a lot of knowledge from this particular section, like how the uh, engine testing is done, the bird strike, how is that affecting, and typically, so there are multiple uh, what do you call videos that professor showed, which showed like how if you are in a dusty environment, how the dust uh, is going to affect your performance, and whether the engine will continue to run even in that dusty environment. So such testings people do by just injecting a huge amount of sand at the inlet. Okay, so that much level of testing people already do. I think a couple of people asked the initial uh, sessions that if there is a dust in the air, how is that going to affect the performance, right? So people typically do all these tests and they will understand how the performance is varying. And most importantly, they should not make the engine should not shut down in such conditions. So based on that, they will provide the requirements on where you can use this engine, whether this engine is compatible with this climate or not. So they will be able to certify it. Okay. So all these things we studied. I'm not going to get into details. It's and I guess a couple of questions are there based on this part too. But since it's theoretical part, I'm just going to leave it on to you. You guys are already experts in theory, so I'm not going to get into that. All right, so that's it. So that's what we studied in the last week, or in general. I hope the entire 12 weeks content is very useful, and it's particularly new for most of the people, and I hope you enjoyed it. So what we will do is we'll continue with our today's problem, the component matching problem with a single spool turbojet engine. So, so this is the single spool turbojet engine, and everyone knows this. You have an inlet, compressor, combustion chamber, turbine, and there is a jet pipe, and there is a nozzle. Okay, and what we are going to do is a single spool turbojet engine is at the ground condition, operating at ground condition, which is the design point for this engine. And T infinity, P infinity is given, compressor pressure ratio, turbine inlet temperature, total pressure loss in the combustion chamber, fuel heating value, and the core engine mass flow rate, everything is given. So for this design point and the efficiencies and losses, in addition, there is also two additional input that is being given. One is compressor characteristics, which is the pressure ratio and the uh, m dot C2 relation, which is corrected mass flow rate through the compressor, m dot C2 relation, and also the efficiency. How the isentropic efficiency also varies with the pressure ratio. So how the efficiency is going to vary with the pressure ratio. Similarly, for turbine characteristics, the m dot C4 and the turbine efficiency, how is going to vary with the pressure ratios across the turbine. Here, for simplicity, here we have considered the turbine characteristics to be constant for the entire pressure range. And however, for compressor, the turbine compressor characteristics are varying. Okay. So now for this design point, I've already this we all are very we are all expert in how to find the performance parameters for the design point. So given the design point, given the engine, we haven't used compressor characteristics or turbine characteristics here, but we all are familiar in solving each and every component, and finally find the pressure, temperature, and velocity at the exit of the nozzle. And from there, you can find the performance parameters such as thrust, TSFC, eta, and also area of the nozzle, and also the velocity at the exit of the nozzle. So this I'm not going to show, that I have already done. These are the parameters. The performance, the area is around this, and velocity is 579.79 meters per second. Thrust is 12.8 kilonewton. TSFC is 0.1171 kilograms per hour per newton. Thermal efficiency is 18%. Okay. Now the question here is calculate T04, thrust, mass flow rate, and fuel to air ratio for the following off design condition. Okay, so this is at design point. Okay, now for an off design condition, here the off design condition is a cruise at 34,000 feet altitude with a Mach of 0.85 and P infinity and T infinity. So if you look back, the design point is at ground condition, which means flight m infinity is 0, and the T infinity and P infinity is 288 and 101.3 kilopascal. Here, for off design condition, you have the flight is flying at 0.85 Mach at 34,000 feet altitude, where the pressure and temperature are 24.72 kilopascal and T infinity is 22 Kelvin. So at this location, what should be my T04? Thrust, mass flow rate, and fuel to air ratio is what should be. So for that, we need to do this component matching analysis. Okay. All right. So first, let me present some of the equations that we studied for the sake of completeness. Okay. So first is mass conservation. M infinity is equal to m dot 2. Okay. So this is just mass. Whatever enters the inlet is going to reach the compressor. Okay. This is a single spool turbojet engine. And the pressure and temperature we know how to find. The compressor and combustor matching. Here the mass conservation is m dot 4 is the exit of the combustor. M dot 4 is equal to 1 plus F times m dot 2. Whatever enters the compressor is going to leave the compressor, and in addition there is no bleed, so whatever leaves the compressor and the fuel is getting added here. So that's why you have m dot F plus m dot 2. This is mass conservation, we all know already. And the pressure P04 is going to be, we are going to write it in terms of pressure ratios. Okay, so P04 by P03 into P03 by P02 into P0. So the pressure ratio P04 by P03 is nothing but the pressure loss in the combustion chamber, which is almost constant in wherever you are. So you can treat that as a constant. And P03 by P02 is something, it can vary. Okay, so that is we are not going to touch. And P02 is determined by the flight conditions and also the P infinity. Okay, so P02 is already known. So from here we can find the exit pressure is a function of, now only unknown here is the pressure ratio across the compressor. It is not same, although for the design point the pressure ratio has been given as 5, but at this at the flying altitude you may not have same pressure ratio. Okay, so that is one thing. So that's a variable. P03 by P02 is a variable, and the temperature ratio is going to be like this: T03 by T02, which is across the compressor, which is also a function of pressure ratio across the compressor. So that is known. And the energy conservation, we know this energy conservation. So I just write it in a different format. So here the energy conservation is going to be in the combustion chamber, right? So m dot what do you call m dot 2 CPC T03 plus m dot f eta BQR is equal to m dot 4 into 1 plus f into CPH times T04, right? So that's the energy conservation. You rearrange them divided by T02. So because that you will know why we are dividing by T02, because it's convenient when we are solving the problem. So then you divide it by T02 everywhere, so that you will end up having energy conservation as in terms of fuel mass flow rate, fuel to air ratio, which is equal to CPH by CPC T04 by T02 minus T03 by T02 divided by QR eta B CPC T02 T04 minus T02. Okay, so now since you did that, T03 by T02 is a function of compressor pressure ratio. So we are trying to express everything in terms of compressor pressure ratio and the throttle value. Okay, so here the throttle value is nothing but T04, right? So since we already know T02, so T04 by T03 we can take it as a throttle value. Okay, so T04 by T02 is the throttle. T03 by T03 is a function of compressor pressure ratio pi c, and other things you already know. Other things are just a constant; it's not going to vary. Okay. Similarly, efficiency of the combustion chamber, we can treat it as a constant. Okay, it shouldn't matter at different temperatures how that is going to vary. We can, in general, treat it as a constant for simplicity's sake. Okay. Then compressor turbine matching, which is basically the energy coupling between these two. So the mass conservation is going to be like m dot C2 is equal to m dot C4 into P04 by P03, P03 by P02 divided by 1 plus f into square root of T02 by T02. So this is nothing but m dot C2 into 1 plus f is equal to m dot C4, right? So it's just a rearrangement of that. Okay, and you also have energy conservation. So this is the temperature ratio across the turbine, and that is going to give you a relation like this. Okay, so now you can see we have expressed everything in terms of T04 by T02, F, and P03 by P02. Okay, sorry, correct, P03 by P02. P04 by P03 is just a pressure loss, so don't worry about it. Okay, and turbine nozzle matching is going to have a mass conservation in this way. So this is coming from the nozzle choking, similar to the turbine. So turbine inlet is assumed to be choked. Okay, and that is why you got this relation, and also you are getting this relation. Okay, so m dot C4, m dot C5 by into P05 by T star STP divided by square root of T05 by T STP is equal to m dot 9, which you can express in this variables. Okay, so based on choking condition, P05 by T square root of T9 and V9 by square root of T9 will have different expression that we already know. If it is choked, it's going to be simply V9 is going to be square root of gamma or T9. So you will have only square root of gamma. Okay, for this. Same goes here. If it is choked, the P05 by P9 relation is going to be based on that. You can update these relations. Okay, anyway, we will solve one problem. So based on choking condition, you are going to have for choked nozzle, this is your expression, and for unchoked nozzle, this is your expression. Okay, this is what I said last. So now, how do we solve this problem? So the hint is going to be for the known flying condition and the diffuser efficiency, which is we know we can find T02 and T02. Okay, as I said, this is our first step. We will find P02 and T02, which is stagnation temperature and pressure. Okay, at the inlet of the air. From there, you choose a compressor pressure ratio. Okay, because these are all interlinked, we do not know what should be initially the compressor pressure ratio. So we need to do it in an iterative way. So initially, what I'm going to do is like we did for prop fan, right? Or a turbo prop engine, right? So we don't know the power split. We know the power split factor, but we don't know what is the exit temperature, right? Exit pressure and temperature. So we did like a, oh, it's not prop. In prop also we did. In the also regenerator cycle we did iterative procedure because we don't know what is the exit temperature of the low pressure turbine, which is going to preheat the air. So similarly, we are going to have, we don't know the compressor pressure ratio. So we choose a compressor pressure ratio and then see whether all the equations are satisfied. If it does not satisfy, change the compressor pressure ratio. That is what we are going to do. So here we first choose P03 by P02 and use compressor map to find m dot C2 and eta C. And once you find m dot C2 and eta C, find tau C and assume F equal to 0. So there are two steps. First, assume F equal to 0. And from the turbine map, you find m dot C4, eta T, and T04 by T2 using the mass flow rate matching. And find the new F from energy conservation of combustion chamber and check whether this and this are matching. If not, you modify the F and continue doing this process until you settle with the correct m dot C4, eta T, and T04 by T2 for the specific F. Okay, and once it matches, then find tau T from the energy matching between the compressor turbine and find gas generated pumping characteristics such as P05 by T02, T05 by T02, and m dot C5. Once you find m dot C5, use pumping characteristics, find m dot C9 based on the appropriate choking condition. And if m dot C9 is equal to m dot C5, then matching is complete. If not, you modify the compressor pressure ratio and make sure this m dot C9 is equal to m dot C5. M dot C5 is the mass flow rate at the exit of the turbine. That has to match with what should be the mass flow rate going through the nozzle. So these two should match. If it matches, then whatever the chosen compressor pressure ratio and the throttle condition is correct. Okay, is appropriate. Okay, if it's yes, then matching is complete, and use that as a throttle condition. You can find other performance parameters such as thrust, efficiency, and other things. Okay, so we will do this for this single spool turbojet engine that we took here. So the off design point is the cruise condition for 34,000 feet, and P02 is 39.9 kilopascal and T02 is 2251.79 Kelvin. I'm not going to go through the details because you already know. I just substituted m dot infinity, gamma C, and eta D here, and P infinity and T infinity is given in the problem. Okay. So now what I'm going to do is, first step is I need to choose a pressure ratio. So I'm going to choose P03 by P02 as 5, same as my design point. You can start from there. So for this pressure ratio, from the compressor map, the corresponding mass flow rate at the compressor inlet and compressor efficiency are 20.165 kilograms per second, and the efficiency of the compressor is 0.8. Okay. So now once you find, we can find P04, which is the pressure at the exit of the combustion chamber, which is around 182.83 kilopascal. And because we know already everything, so P04 by P03 is the pressure loss, which is 6% in the combustion chamber. So you can substitute all these values, it will give you 182.83 kilopascal. The other one you need to find out is temperature ratio across the compressor, because that is going to tell what is the amount of fuel that I need to add it in the combustion chamber. So that tau C is going to be around 1.6950. Now, the normal operating line can be obtained from the mass flow rate matching. Okay, so the mass flow rate matching is nothing but m dot 4 into 1 plus f into m dot 2. So now m dot 4 is nothing but choking condition. We have assumed that turbine inlet is choked. So from there we know we can write m dot C4 is equal to 1 plus f into m dot C2, right? And m dot 4 is nothing but m dot corrected mass flow rate times pressure ratio divided by square root of temperature ratio. So that's what, if you rearrange, you will end up having this. Okay. For detailed derivation, please refer to Professor Chetan Mistri's lectures. So now m dot C4, because we know only corrected mass flow, we don't know the exact mass flow rate. We are going to find it. Okay. So one assumption here is we have assumed that the turbine inlet is choked. So from that assumption, we were able to make this, and we can convert this m dot 4 into m dot C4 in terms of pressure ratio and temperature ratio. All right. So we have to take an initial guess for F. F you can calculate from 0. But I'm going to choose this weird number 0.0188. The reason you will know, obviously this F is going to match all the things. Instead of wasting your time on doing this iteration, I thought you can start from F and you will end up converging at this point. Okay. So now you take an initial guess of F equal to 0, or you take my value 0.0188. You substitute it in the T04 by T02, which is the throttle setting, and that will give you around 4.1894. And the fuel to air ratio, once you know the throttle setting, you will end up having 0.0188. So that's why I chose the initial guess as 0.0188. If you start with 0, you will have a different F here. So once you have different F here, you go back, substitute in the T04 by T02, this expression, T04 by T02, okay, and which is basically the mass flow rate matching. You substitute in this expression, and again, once you find T04 by T02, you substitute in the fuel to air ratio to check whether that is matching. Okay, so that will end up having, that will give you 0.0188 as your guess value. So same as our initial guess, so we are good. We will go forward with this fuel to air ratio, and the next is energy conservation between compressor and turbine to find the temperature and pressure ratio across the turbine. Okay, so for that we know F, we know the throttle setting. You substitute that to find the temperature ratio, which is 0.8553, and for that the pressure ratio is 0.4804. That is how the pressure has reduced in the turbine. Okay. Now, pumping characteristics of the pumping characteristics becomes the m dot C4 by m dot C2 is nothing but the pressure ratio divided by square root of temperature ratio, and that is around, m dot C2 is around 17.22 kilograms. Okay, so this is one importance. This m dot C5 now has to match m dot C9. Then if it matches, it's good. Our matching is complete. If not, we need to repeat this calculation by changing the pressure ratio from first. Okay. So similarly, the pressure total pumping characteristics P05 by P02 is around 2.2578. Okay. So from there, P05 is 85.74 kilopascal, and from there T05 is 902.21 Kelvin. Okay, and now you can do turbine nozzle matching, and so basically we have to check whether the critical condition is achieved, and first we will check that, and if it is higher, the nozzle is choked. Therefore V9 and P05 by square root of T9 will find, and once you find them, you substitute it in the mass conservation law for m dot C9. Okay, so that comes around 17.26 kilograms per second. So this, okay. So now this is equal to whatever we got from the turbine characteristics, which was before. So you see here uh, from the turbine characteristics we got m dot C5, m dot C5 is 17.22 kilograms per second. And if you continue it and do the nozzle matching, you end up having 17.26 kilogram per second, which is almost close. Okay. So if you want, you can adjust the pressure ratio slightly, let's say like 5, right? We took 5. If you want to match this exactly, you slightly vary like 5.01, 5.05, or 4.95. You can change that, but that doesn't make much sense. 7.2 and 7.2 is almost similar, so don't need to worry. So now since this is same, our matching is complete. So that's why I chose 5 as my initial guess. You can start with 4 and you will end up having matching will not be complete, so you will rise to 5 anyway. Okay, so this is like an iterative process. Here since I did the calculation before, I know what is the value, so I just provided it here. But in your problem, let's say in future, if you want to try a new problem like this, then you have to do this iteration by yourself. Okay. So therefore, from the corrected mass flow rate dictated by the nozzle is 7.26, but the corrected mass flow rate from the turbine exit is 7.22. So they are almost equal. Therefore, the choice of pressure ratio selected at the start of the problem is correct. Okay. And if this does not match, you change the pressure ratio and you repeat the calculation. Okay. That is known. So finally, the operating line, what should be my T04? We found T04 by T04. Now you just multiply that with the T02 to find T04, which is 1055 K. Okay, so this must be your TT4 at the flying condition. And the fuel to air ratio is 0.018, and m dot infinity now you can find, given you know the temperature and pressure, so you can find it out to be 8.0757 kilogram per second. That should be the m dot infinity that should enter the engine. Okay, and the performance V9 you can find out now. Since you know T04, you can also find T9, you can find everything. You can find V9 to be 543.7 meters per second, P9 45.88 kilopascal, and therefore you can find the thrust to be the same thrust relation. You substitute these values, you will end up having 3.9867 kilo. Okay. And similarly, TSFC, you multiply F, m dot infinity and T, you will end up having 0.1371 kilograms per hour per Newton. Okay. Second. Okay, why has it stopped? 1 second, give me. Yeah, okay. All right. So finally, efficiency also you can calculate, and the efficiency comes out to be around 20.3%. Okay. All right. Now we will do side-by-side comparison. So for the design point, now for the off design point, you will not find area. Even if you find, it's going to be same. That's the whole point of this analysis. So you can find off this. So you can find the area. It will be same. So area here is going to be same because it is already designed. So at design point, your velocity at the exit is 579.79 meters per second. During the cruise condition, the same velocity at the exit is reduced. And similarly, thrust at the ground condition is high, around 13 kilonewton, and here is around 4 kilonewton, which is expected. At the cruise, we will have low. At the ground condition, we will have the highest thrust, right? And the TSFC has slightly increased from 0.1171 to 0.1371, and the thermal efficiency has increased from 18.2 to 20%. M dot infinity has reduced, which is expected because you are flying at a very high altitude, but you are flying at a much faster rate, so that's why you see reduced by half, okay? Around 8 kilograms per second. And the T04 for the design point is 1200 Kelvin, and for the off design point during the cruise, you do not need that much high temperature, so the turbine is also safe, which means during takeoff for a small short duration, you will inject a lot of fuel to reach 1200 Kelvin, or forget about the amount of fuel, but you will have an hot exhaust from the combustion chamber, which is going to go through the turbine, and that is going to give you very high thrust during the takeoff. But during the cruise condition, you will reduce the temperature, and the turbine will also, the thermal load on the turbine will also reduce. Okay, so from 1200 Kelvin, it has reduced to 10,055 Kelvin. All right. So this is the whole uh, uh, component matching problem that although professor didn't solve it, but professor wanted me to solve, so that you will get a good clarity on how to uh, do off design point calculation. So till now we did only performance calculation for a given design point or for a given engine configuration. Now, for a given engine and its design point, will also be familiar with doing off design point calculation. So now the next step, organic next step is, given this your thrust and TSFC, you should check from the aircraft vendors, or for example design aircraft design people, whether this thrust is enough for running the for flying the aircraft. Okay, so this is the thrust you will get from the engine. So for here, if you give 8 kilograms per second as an inlet, at the inlet, you will end up having thrust and TSFC as this. Okay, so but we don't know whether this thrust is enough for the flight. Okay, so when flight is flying at 8.85 Mach, whether this thrust is enough, or for example when it is at the cruise, or when it is in the taxi, or when is it approach and landing, these are the thrusts we get, but whether this thrust is enough from the drag and lift perspective, and also from what you are carrying in the flight, whether it is a cargo flight or a passenger aircraft, uh, you will know what is the weight and also the fuel total takeoff weight or total weight of the aircraft. From there, you should find out what is the total drag and thrust required for the aircraft, and whether the thrust is matching with the engine thrust. Okay, typically, yeah. So if that matches, then your engine is good to go. You can put it in the aircraft and you can fly it. Okay? In a sense, that is, you can clear one step and you can go for actually designing and also testing the engine, or actually manufacturing and testing the engine. So all these calculations that we do has to come before manufacturing the engine. Okay, so typically that is what aircraft vendors also do. Once they design the, for example, Boeing will, Boeing or Airbus will say that I am designing this 250 or 300 passenger aircraft, and I'm going to fly from here to here. So I need my flight profile would look something like this, and my thrust profile at various sections of the flight profile. These are the thrust I need to satisfy, and can you design an engine and give it forward? So that is what the aircraft vendors will say, and the engine developers like our engine manufacturers like Pratt and Whitney, or GE, Rolls Royce. So what they do is they take these inputs, they first design it for a design point, and they'll find where maximum thrust is required. So for that, they design the engine, and they modify the engine to match all the thrust. Those are off design point calculation. That is what we did today. Once they match, once they know that these parameters would work for work in the actual environment, then they go for manufacturing. And once they manufacture, they test it for all these off design conditions, and once they test it, once they certified it, then they will give it to FAA, and they will certify it, and once they certify it, they directly install it in the aircraft and they will test it more. Okay, so that's what the final part that professor discussed, engine testing. Okay, so before manufacture we have to do all these calculations, and this is just a basic calculations that I showed, but the calculations that they do for different profiles, different thrust conditions, it's going to be very intensive. Okay, so but this is just a starting point. Okay, all right. So I hope this helps you understand better the component matching, although because we had only 1 week to cover this particular topic. Uh, so I hope you understood that. And anyway, you don't need to worry much about these calculations to be asked. I don't think it's going to be asked. Uh, he might, I think in final uh, exam you might end up having questions in terms of equations or basic concept, like how these things are. So those kind of questions, although you would have seen it in the assignment 12, so such questions you can expect from this topic. And yeah, all right, thank you very much. Thank you for showing interest in joining this course and also taking time to read this, study this subject. I hope it is useful for your career. If you have any doubts, please feel free to reach out to me. You can also use the common forum to reach out. I hope uh, this course has given you uh, confidence on aircraft Aeroengine gas turbine cycles. All the best for your exams. Thank you very much for joining. Thank you very much for people who are going to see this in YouTube. Yeah, as usual, if you have any doubts, please feel free to reach out. But I guess we will not meet anymore. Uh, like considering for this course. Okay. All right. Thank you, Krishna Kumar. I will anyway stay back here for another 1 hour or so. You can feel free to leave.